Okay, we don't skip many sections in the book, but this is one point where we've skipped something. We are skipping the lens maker's equation that's under the focal length section of your book. This is important for people that that create glasses, that you understand this if you're going to go to optometry school, but I don't think any of you are, because there's another class you need for that. Anyway, we're going to skip that section. The power of a lens describes the strength of a lens. If you've ever gotten reading glasses or if you wear glasses, they might talk about the power of your prescription. And it describes the strength of a lens. A lens with a larger power will cause the light to bend more than a lens with a smaller power. You can think about how these lenses might look. Like, let's imagine that I have a lens that's like this, and then I have a lens that has a much smaller focal length. Like, see, this one has a big focal length. I might remember these are like they're part of a sphere. And so the focal length for this would be like out here. But for this one, the focal length would be like right here. And if I have light rays that are coming in parallel to one another, they're going to focus at that point. But here, they focus at that point. So this lens right here has the bigger power because it's caused the light to bend more. So this one has the larger power. Just because it's caused the light to bend more. The power is a function of the focal point. It's equal to 1 over f. So if the focal point goes up, the power goes down. So while this one has a large power, it has a small focal point. That just means that this distance, f, is smaller than that distance, f. They're inversely related. And then vice versa. If f goes down, then that means that the lens will bend light more, so the power will go up. Oh, I've already drew those pictures. So the two lenses with different focal lengths. I'll do it one more time just so you see. So this one has a big focal length. Light coming in will bend way out here. This one has a smaller focal point, so light coming in will bend right there. Big focal point, small focal point, or smaller rather. Small power, big power. So those of you with lenses that have a really high power will actually, you can sometimes see how they're just thicker than other lenses. Now, optometrists are really good at designing lenses now, and so even a lens with a really high power can be created in such a way so that it's not really that thick. My wife is that way. Her eyesight is pretty bad, and so she has to have a lens that bends the light a lot before it enters into her eye. So her glasses have a really high power, but she gets these special thin lenses so that they just don't look so thick. When I was a kid, we used to make fun of people, and you shouldn't do that, but we used to make fun of people with really bad eyesight, and we would say that they had Coke bottle glasses, because we used to get Coke in these bottles that were really wavy, thick glass, and their glasses looked like a Coke bottle. But you shouldn't make fun of people that way. In fact, you can't really make fun of them that way anymore because they don't make glasses in that way. Okay, so let's go ahead and look at the thin lens equation. The thin lens equation is this, and I'm going to show you what you need to know about this, so don't freak out about it. 1 over DO plus DI plus 1 over DI. First of all, let me define to you what DO and DI are. Here's you. Sort of looks like you. Here's your bathroom mirror. This distance between you and the mirror is the object distance, DO. So DO is the object distance. And then here's the image of you, which is behind the mirror. I try to do it with a dashed line. But that distance is the image distance. di. So di is the image distance. Now for a flat mirror, the image distance is equal to the object distance. But that doesn't have to be true. So for other items, like say a camera, imagine if we have a camera. Oh, let's run out of space. Here's my camera, there's my lens, here's your object out here. This would be DO. That's your object distance. But this back here is my film or my chip or whatever, wherever the light is collected. This distance is my image distance. So my image distance and my object distance don't have to be the same. In fact, they often are not the same. They're always the same for a flat mirror, but usually not the same for a curved device like a lens. So for most instruments, you can change either the object or image distance. And for example, cameras. With a camera, you can change this distance, that's the object distance, just by moving the camera closer to the subject, or that subject moving closer or farther away. But you can also change the image distance. You can make that lens move closer to or further away from the imaging surface, the film or the CCD, the chip in the camera. Microscopes, for example. Oh, let's see, can I draw a microscope? I don't know if I can. This is the table where you put stuff, and then this is the lens. Then you can change this distance, which is DO. This is a microscope, I'll tell you. And or you can change this distance, which is the DI. So you can move the lens up and down, or you can move the table up and down. With the eye, however, the image distance is fixed. It's always fixed. So if you imagine an eye, I'll imagine the eye as a lens with some imaging surface at the back. So this is where the image forms, and so the distance from here to here is our image distance. And that image distance is always fixed. So the eye cannot change the image distance. The only thing it can change is the object distance if you're changing what you're looking at or the focal length. So the eye will change the focal length. Notice what happens to F if the object distance changes. I'm going to rewrite this equation. 1 over DI equals 1 over F minus 1 over DO. So what happens if DO goes up? What happens to F? Well, if DO goes up, then F must increase. Or if DO, the object distance, goes down, then F must decrease. So this is constant. If this goes up, this has to go up. If this goes down, this has to go down. F is proportional to the object distance. If one of them goes up, the other one goes down. If F goes up here, that means that my lens will go from being big in the middle to being skinny, like that. That is an increasing focal length. We saw that before. If F goes down, that means that the eye goes from being thin to being wide in the middle, like that. That is a decreasing focal length. And we'll see how in the eye that happens. The eye is really pretty phenomenal that it can change its focal length in such a way. We just don't really have optical devices that do that. So the eye might be my favorite organ of the human body. So to see objects close to the eye, the focal length must decrease. That means that the lens is wider. in the middle. To see objects far from the eye, the focal length must increase. The lens is thinner. As I said, DO is proportional to F because DI is constant. Our image distance for the human eye doesn't change. I can sketch these before, but let's say this is my lens. Oh no, I don't need to sketch them again. I won't sketch them again, so you can just go back. Okay, what is the focal length for an object a very large distance away? So if I think about that equation again, if DO gets really, really big, that means that DO basically goes to infinity. What happens to this term? Well, if I make the denominator of this number really, really big, 1 over a gazillion, then that term basically goes to 0. So if D gets really, really big, then F is equal to the image distance. So in the human eye, if I'm looking at something that's really far away, the focal length of this lens is going to be right there. That will be the focal length. That's for something that's far away. But if I'm looking at something that is nearby, then the focal length has to be right there. Okay, we'll get into that more as we see this chapter unfold in the A and P section.